Hello, my name is Napat Tatiyakaroonwong and my partner Patorn Patmuk. Here we'll be presenting the problem of minimum edit distance. So let's first start by defining the edit operations. So there are a total of three edit operations: insert, delete, and substitute. So for insert, it means that you when you have some string, and then you say insert some character, you put the character into the string anywhere in the string, so in any position. For the delete, it's the exact opposite. You actually remove the character from the string, and here from the substitute, it's just replacing some character by another character. And also, after defining these edit operations, we'll be giving it a cost. uh, Actually, you can use any cost that you want. It doesn't change how the algorithm work, but it will change what is the minimum edit distance of some string. So in this video, we'll be using the cost of one for insert and delete and two for substitution. So now let's define the problem, which is the edit distance. So let's say you have two string, A and B, and you want to edit the string A using those edit operations in such a way that we can transform A into B. And the total cost of doing those operations is called the edit distance. So for example, we want to transform horse into the word moose. So first we can start by substituting h with m, and horse will become morse. And after that, morse we will substitute r with o, then morse will become moose, and there we get our word moose. And you can see that there's two substitution happens, and therefore the edit distance for this transformation is 2, and time cost of the substitution, which is 2, and therefore the answer is 4. The minimum edit distance is easily just the lowest cost of operations possible that you can transform between a string pair. So now we'll be talking about how we can use the recursive structure to actually define and find a way to solve this problem. So if you look, let's start at the root of this tree. We see that this is our target. We want to find this. Um, Now we can define this transformation. We can think of it as either one of the three ways. First way is insertion. So it's just BOY transforming into LO, and then you insert L at the end, so it become LOL. Um, this transformation right here, let's say we know the minimum edit distance of this transformation, then the word boy into LL is just that minimum edit distance plus the cost of insertion, which is 1. So it's just boy minimum edit distance of boy to low, and then plus 1. Uh, this the same goes similarly for BO to LL. So instead of inserting, you do deletion of the Y character like this, and you can think of it as the word boy to LL of delete Y, and then we get this minimum edit distance, and then so it's the minimum edit distance of BO to LL plus 1, which is the cost of deleting Y. Now for substituting Y with L, we have that we can start from the word boy to LL to BO to LO, and that is actually the minimum distance, and then add with the cost of substituting y with l. So this will be the minimum distance of this plus 2 is this. So now we compare these three paths of the tree and check if what is the minimum value from this tree, and there we get the minimum edit distance of this. Now you can see that this work recursively with all the string that is the child of boy to LL. And you can see that it's the same algorithm applies recursively to until the base case, which is actually just some word transformed into an empty string. So when you know that some word transformed to an empty string, you know that it's just you to get that you just delete 3. So that means the cost of those operation is 3 times the cost of insertion, which is 1, and 3 times 1 is 3. So the same go for two characters like this, and for empty string to empty string it is 0, as you can see right here. Um, Now since we know the base case and that is the leaf node, and now let's see, you can see the pattern that there is very many overlapping problems. So you can see BO to empty string like this, BO to L, BO to L, BO to LO, and BO to LO. So what this suggests is that since this problem has a recursive structure and that there is many smaller subproblems that is overlapping, it suggests that we can use what's called dynamic programming. So in this approach, if you want to use the algorithm to create this approach shown here, this is a top-down approach, and you can do this by memoization, which is just caching the answers into some map or some array and then reusing it if it already exists in the cache. So that is the memoization method. However, we'll be talking about the tabulation method today, so it's a bottom-up approach. And before we go into that, let's look at the recurrence relation of this definition mathematically. So let's say we define d of ij as the minimum distance of the string pair a from index 0 to I and b from 0 to I. So this basically means the first character, which is at index 0, to the character before index I. So index I minus 1. This is exclusive. Um, So after we define this problem, we then set the initial conditions that we explained earlier, that the some characters transform into an empty string or some empty string turn into some string. It's going to be the number of the characters, so it's straightforward. D from 0 to 0 is the empty string, to J is J, and D from I to 0 is I. Okay, so now for the other dij, the recurrence relation is just the minimum of the three path taken. So the first one, this one, is actually just insertion, which is, you can see, is the function d of ij minus 1, and then you plus 1 to the cost of insertion. And then the next case is obvious, which is d I minus 1 of j plus 1. So here it's just like insertion, but instead it's deletion. So it's d of I minus 1 and j. Now for the middle case, there are actually two ways and two cases, which is in the case that obviously if a and b at index I minus 1 and j minus 1 respectively is not equal, it is obviously just the d of I minus 1 or j minus 1 plus 2, right? 2 is the cost of substitution. But in the case that the character at I minus 1 of a and character of j minus 1 of b is equal, it means that they are the same character, right? But when you take this part down, you are basically saying you are substituting O with O, which is weird and wrong because you don't have to substitute O with O. It's just the same character. So you can treat that as a cost zero, which means you don't do any operations and you just take on the value of d of I minus 1 and j minus 1 directly. And then we compare these three values and find the minimum. And then we will get the recurrence relation of the ij. Finally, we will get our answer, of course, at I is equal to length of string A and J is equal to length of string B. So we can start doing a the bottom-up approach tabulation method right now. So I will show you the code. Okay, so here's the code for the minimum edit distance. So it takes two input, which is string 1 and string 2. First, we find the length of string 1 and string 2, which we define as m and n respectively. Now we will be initializing our minimum edit distance table, so that's what MED stands for. Here is where we define our initial conditions. So just like what we said earlier. Now after defining these initial conditions, we just loop through the rest of the table, which is from index 1 to m plus 1 exclusive and 1 to n plus 1 exclusive, and we go to all these three constellations. So if this one is actually um, the deletion, so it's just plus 1. This one is the condition of substitution, which is if the character is equal, it take the value directly of minus 1 j minus 1, but if it is not, it's just the same but plus 2, which is the cause of substitution. This is for the insertion. So with this three paths, we find the minimum, and then whatever is the minimum value, we put it into the MED table as ij. After looping through all the table, our minimum edit distance will be stored at the index m and index. So now let's look at our example, which is turning the word horse into boss. So actually, the minimum edit distance here is when you transform h into b, right? So that is 2 for sub, and next one is you transform, where you can let's say you transform R into S, that's 2 for sub, and then you transform, sorry, not transform, you actually delete E, it's 1 for delete. So the total is 2 plus 2 plus 1 is equal to 5. Let's verify if our answer is correct. It is indeed 5.
Next, we are going to find the minimum edit distance from the example input string and output string, which in this case we will use our full names. First, we have to create a table with the input string on the first column and the output string on the lowest rows. But we will read from the bottom to top for the input string. So to interpret these tables, we look at the orange tables. It means that this table will store the value of minimum edit distance from the input string NAPA to the output string of hyphen, or it means empty strings. This orange cell will store the value of minimum edit distance of input string NA to the output string PA. And ultimately, our goal is to find the values of the green cell, which is the minimum edit distance of input Napat and output Patorn. To start off, we start with the hyphen rows. We know that if we have the word of length n and we just want the output to be an empty string, we just delete all of them. So it will cost n operations to delete all of them. So the value will be equal to the length of the word. For example, if we have input string NAP and we want output to be just empty, we just delete 3 times. The same goes for the rest as well. Next, we have to fill out the rest of the tables. So we look at the D11. From the algorithm we explained earlier, we will consider 3 cells earlier. So we will choose the minimum of D10 plus 1, D00 plus 0 or 2, depend on if the character on that row and column is the same or not. And the last one we will choose the minimum from is D01. So in this case, N and P is not the same characters. So we choose the minimum of 1 plus 1, 0 plus 2, and 1 plus 1, which are equal to 2, and we will choose 2. So the minimum edit distance from N to P is 2. We fill out the rest of the third row from the bottoms, and we can see that to edit from input N to output PATOR, we have to edit 6 times. But for the D16, we see that both characters are N's. So we choose the minimum of 6 plus 0, 6 plus 1, 5 plus 0 because both characters are the same, and 6 plus 1 of the D06. So the minimum will be of 7, 5, 7, so we will choose 5. So in this case, we can see that the minimum distance is only 5. We do the same for the rest of the tables, and this is the output. We can see that the value of 5 on the from the top right mean that we have to edit 5 times from the word Napat to Patorn. And as we did it earlier, we can see that the time complexity will depend on the length of input and output that we want, because we have to compute the values of the whole tables, which is equal to A times B values. So the time complexity will be of all ABs. And since we have to store the value of every values in the tables, the space complexity will be OAB as well. And last, onto the real-world applications. We can use minimum edit distance for the auto corrections and spell checkings, because if we have a libraries of the correct spellings of word and we compare it to the user's input, we can suggest the word that have the minimum edit distance to the user so they can choose to change it or not. Next, we can use this for plagiarisms. Since plagiarism is just copy and paste from the authors and then paste it on your own work, we can check that if this student is copying homework from others or they write on their own. If the edit distance is very low, it has very high chance of them copying others. And we can also use to check the DNA sequence alignment. And like if we have DNA string, we will consist of A, G, C, T, which is only 4 on a very long string. We can use minimum edit distance to find the most similar string of all of them. And last application is the natural language processing. This can help computer to understand what human speaking better, because humans don't always have perfect pronunciation. So they can use minimum edit distance to find the closest word that humans are trying to speak and try to understand and to improve how to listen to human as well.